In computer science, a programming language is said to have first-class functions if it treats functions as first-class citizens. Specifically, this means the language supports passing functions as arguments to other functions, returning them as the values from other functions, and assigning them to variables or storing them in data structures. Some programming language theorists require support for anonymous functions as well. In languages with first-class functions, the names of functions do not have any special status, they are treated like ordinary variables with a function type. The term was coined by Christopher Strachey in the context of functions as first-class citizens in the mid-1960s. First-class functions are a necessity for the functional programming style, in which the use of higher-order functions is a standard practice. A simple example of a higher-ordered function is the map function, which takes, as its arguments, a function in a list, and returns the list formed by applying the function to each member of the list. For a language to support map, it must support passing a function as an argument. There are certain implementation difficulties in passing functions as arguments and returning them as results, especially in the presence of non-local variables introduced in nested and anonymous functions. Historically, these were termed the fun-arg problems, the name coming from function argument. In early imperative languages, these problems were avoided by either not supporting functions as result types or omitting nested functions and thus non-local variables. The early functional language Lisp took the approach of dynamic scoping, where non-local variables refer to the closest definition of that variable at the point where the function is executed, instead of where it was defined. Proper support for lexically scoped first-class functions was introduced in Scheme and requires handling references to functions as closures instead of bare function pointers, which in turn makes garbage collection a necessity. Concepts. In this section we compare how particular programming idioms are handled in a functional language with first-class functions compared to an imperative language where functions are second-class citizens. Higher-order functions. Passing functions as arguments in languages where functions are first-class citizens. Functions can be passed as arguments to other functions in the same way as other values. In the language Haskell, map to a to b map f equals fx. Map fxs languages where functions are not first-class often still allow one to write higher-order functions through the use of features such as function pointers or delegates. In the language C, void map int x size _tn for x I equals f. When comparing the two samples, one should note that there are a number of differences between the two approaches that are not directly related to the support of first-class functions. The Haskell sample operates on lists, while the C sample operates on arrays. Both are the most natural compound data structures in the respective languages, and making the C sample operate on linked lists would have made it unnecessarily complex. This also accounts for the fact that the C function needs an additional parameter. The C function updates the array in place, returning no value. Whereas in Haskell data structures are persistent, the Haskell sample uses recursion to traverse the list, while the C sample uses iteration. Again, this is the most natural way to express this function in both languages. But the Haskell sample could easily have been expressed in terms of a fold and the C sample in terms of recursion. Finally, the Haskell function has a polymorphic type. As this is not supported by C, we have fixed all type variables to the type constant int. Anonymous and nested functions. In languages supporting anonymous functions, we can pass such a function as an argument to a higher order function. Main equals map 1, 2, 3, 4, 5. In a language which does not support anonymous functions, we have to bind it to a name instead. Int f, return 3 x plus 1, int main, non-local variables and closures. Once we have anonymous or nested functions, it becomes natural for them to refer to variables outside of their body. Main equals letter equals 3b equals 1 in map 1, 2, 3, 4, 5. If functions are represented with bare function pointers, it is no longer obvious how we should pass the value outside of the function body to it. We instead have to manually build a closure, and one can at this point no longer speak of first-class functions. Type def struct int asterisk a int asterisk b closure underscore t void map for x I equals int f return of asterisk x plus b void main. Also note that the map is now specialized to functions referring to two ints outside of their environment. This can be set up more generally, but requires more boilerplate code. If f would have been a nested function, we would still have run into the same problem, and this is the reason they are not supported in C. Higher order functions. Returning functions as results. When returning a function, we are in fact returning its closure. In the C example, any local variables captured by the closure will go out of scope once we return from the function that builds the closure. Forcing the closure at a later point will result in undefined behavior, possibly corrupting the stack. This is known as the upwards funarg problem. Assigning functions to variables. Assigning functions to variables and storing them inside data structures potentially suffers from the same difficulties as returning functions. F integer 2 integer f equals letter equals 3b equals 1 in map. Equality of functions is one can test most literals and values for equality. It is natural to ask whether a programming language can support testing functions for equality. On further inspection, this question appears more difficult, and one has to distinguish between several types of function equality. Extensional equality. Two functions f and g are considered extensionally equal if they agree on their outputs for all inputs equals g. Under this definition of equality, for example, any two implementations of a stable sorting algorithm, such as insertion sort and merge sort, would be considered equal. Deciding on extensional equality is undecidable in general, and even for functions with finite domains often intractable. For this reason, no programming language implements function equality as extensional equality. Intensional equality. Under intensional equality, two functions f and g are considered equal if they have the same internal structure. This kind of equality could be implemented in interpreted languages by comparing the source code of the function bodies or the object code in compiled languages. Intensional equality implies extensional equality. Reference equality. Given the impracticality of implementing extensional and intentional equality, most languages supporting testing functions for equality use reference equality. All functions or closures are assigned a unique identifier, and equality is decided based on equality of the identifier. Two separately defined, but otherwise identical function definitions will be considered unequal. Referential equality implies intensional and extensional equality. Referential equality breaks referential transparency and is therefore not supported in pure languages, such as Haskell. Type theory. In type theory, the type of functions accepting values of type A and returning values of type B may be written as A, B or bar. In the Curry-Howard correspondence, function types are related to logical implication. Lambda abstraction corresponds to discharging hypothetical assumptions, and function application corresponds to the modus ponens inference rule. In category theoretical accounts of programming, the availability of first-class functions corresponds to the closed category assumption. For instance, the simply typed lambda calculus corresponds to the internal language of Cartesian closed categories. Language support. Functional programming languages, such as Scheme, ML, Haskell, F#, and Scala, all have first-class functions. When Lisp, one of the earliest functional languages, was designed, not all aspects of first-class functions were then properly understood, resulting in functions being dynamically scoped. The later common Lisp dialect does have lexically scoped first-class functions. Many scripting languages, including Perl, Python, PHP, Lua, TCL, TK, JavaScript and IO, have first-class functions. For imperative languages, a distinction has to be made between ALGOL and its descendants such as Pascal, the traditional C family, and the modern garbage-collected variants. The ALGOL family has allowed nested functions and higher-order taking function as arguments, but not higher-order functions that return functions as results. The reason for this was that it was not known how to deal with non-local variables if a nested function was returned as a result. The C family allowed both passing functions as arguments and returning them as results, but avoided any problems by not supporting nested functions, as the usefulness of returning functions primarily lies in the ability to return nested functions that have captured non-local variables, instead of top-level functions. These languages are generally not considered to have first-class functions. Modern imperative languages often support garbage collection, making the implementation of first-class functions feasible. First-class functions have often only been supported in later revisions of the language, including C# 2.0 and Apple's blocks extension to C, C++ and Objective-C. C++11 has added support for anonymous functions and closures to the language, but because of the non-garbage collected nature of the language, special care has to be taken for non-local variables in functions to be returned as results. C++, C++11 closures can capture non-local variables by reference, by copy construction or by move construction. The former potentially avoids an expensive copy and allows to modify the original variable but is unsafe in case the closure is returned. The second is safe if the closure is returned but requires a copy and cannot be used to modify the original variable. The latter is safe if the closure is returned and does not require a copy but cannot be used to modify the original variable either. Java 8 closures can only capture immutable non-local variables. Lisp lexically scoped Lisp variants support closures. Dynamically scoped variants do not support closures or need a special construct to create closures. In common Lisp, the identifier of a function in the function namespace cannot be used as a reference to a first-class value. The special operator function must be used to retrieve the function as a value. Evaluates to a function object. #foo exists as a shorthand notation. To apply such a function object, one must use the funcall function. Python explicit partial application with functools.partial since version 2.5, and operator.methodcaller since version 2.6. Ruby the identifier of a regular function in Ruby cannot be used as a value or passed. It must first be retrieved into a method or proc object to be used as first-class data. The syntax for calling such a function object differs from calling regular methods. Nested method definitions do not actually nest the scope. Explicit currying with